So I will begin with a word of prayer. Let me get started. Dear Heavenly Father, we thank you for this day. I thank you for these students, and just pray that you guide our work today. Help us to, again, glorify you in what we do. Again, I just ask you to encourage the students that are struggling just to do their best, Lord. And we just pray again, Lord, that you be glorified in what we do this day, Lord. In your name I pray. Amen. Okay, so today we are talking about logarithms and exponentials. So I guess I should probably look at a few of them with you, right? And so I'll just use the projector here for just a minute. Just so we can look at some. Because there are certain aspects of the graph of the exponential which so let me, before I plug the computer in here, just remind you, definition, f of x equals to a to the x, where a is positive and a is not equal to 1, is an exponential function. So if I talk about exponential function, I'm talking about that. And because this function is 1-to-1, it has an inverse function, and the name for that inverse function is the logarithm. So f inverse of x, in this case, is defined to be log base a of x. All right. So this is log base a function. So the two equations which sort of define these is, one of them is the a to the log base a of, let's say, y is equal to y, and log base a of a to the x is equal to x. So the equation on the top is true for y greater than 0, and this is for any real x. All right, so let me take a look at some of those here. Here we go. So here's the top hat, 5571, while I'm at it. Right? So let me open up Desmos here for a minute. So I think that this is, for me, this is the easiest way to look at things. If I've got a computer around and I just want to take a quick look at some graphs and explore, it's hard to beat this. So here, let's try it out. Y equals a to the x. We'll add a slider. There we go. So what happens when you put a equal, why do I rule out a equals to 1 in what I wrote over there? Do you see why? What's the graph of 1 to the x look like? Right, it's this. So this is, we can't have base 1. It's not interesting, yeah? But if we make the base like a little bit bigger, 1.1 for example, as you can see, now we've got something that goes up like that. Now, here, let me put in a reference here. So I'm going to put in y equals 2 to the x so we can kind of track the other cases relative to that. All right, so look at here. Now we have y equals 2 to the x is the green graph. And right now I've got the 1.2 power. See what happens? The 1.2 power grows slower than the 2 to the x, right, if we're positive. But it goes to 0 faster, rather slower, if we're to the left, right? So you've got this, and then we can see what happens if we raise the base. What happens? Like I go up here. See, now I'm at 1.6. What's going to happen once I get to 2? We're going to match, right? Then if I go bigger than 2, we've got, here's, for example, here's 3 to the x. See that? 3 to the x is now the red graph. So let me adjust the slider here for a second. Let's just go from 0 to, let's say, 4. And I'll do it in step sizes of 0.01. There we go. So what we're looking at here is the red is animating. Do you see something? There's something really dramatic happening for certain values of a, right? What makes it turn over, so to speak? Right. Not a is not negative here. So I'm making a go from 0 to 0 to 4. And so if you look at it, the a which are below 1, right? See, if once we get below 1, it sort of turns over, right? So, but it's, let me just stop it here. See what happens here? Once we get to 1, it's the boring case. And then past that, you're the other way. See this? Like, for example, here is 0.5. What's 0.5 relative to 2? 0.5 is 1/2, right? So this is, the red graph is 1/2 to the x. The green graph is 2 to the x. See? So this is this is pretty much what happens. Now all of them, look at it. It doesn't matter what exponential you're talking about. It goes through the y-intercept is 1, right? They all meet there. Okay? So these are the graphs, right? Now you can look in your textbook. I'm sure he has, nice static pictures there for you to look at. But I think it's nice to get this out and just kind of play around and see what it looks like. Yeah. Now, what's e to the x? You may have seen that in your science classes, perhaps. Have you guys seen e to the x? Do you know what this is? What's e to the x? Let me look at a couple things here. Let's look at, I'm going to turn this one off. Let's look at 2 to the x, and let's look at y equals 3 to the x. See that? So the 3 to the x is the blue one. The 2 to the x is the green one. All right? And if you want to, you could study the slope of the tangent line at the origin. Now, I know you guys don't know what a tangent line is because this isn't calculus and we haven't defined it, but some of you have had calculus in high school, right? Probably. And if we zoom in a bit, you can kind of imagine looking at a line which is, just like touching the graph. And if you looked at that, you could look at a couple points for the 3 to the x. And like if you go from, say, 1, let me zoom out a bit. It's fairly easy to see if you go from, you can kind of get a sense of this slope by, say, oh, I don't know, it's roughly speaking the same slope as like a line that goes from here to here, right? So that's over 1 up to. So the slope of the blue line is, it's around 2. It's a little bit less than 2 at the origin. The slope of the green line, on the other hand, if you look at it, we're going over 1, right? And we're going up less than 1. So the slope of the green line is less than 1. So you have the blue line, which has a slope greater than 1. You have the green line, which has a slope less than 1, right? Which means there's got to be some kind of exponential function between those two, which actually has a slope of 1 in between them, all right? That's what we call e to the x. E to the x is the graph of it's the exponential function that has slope 1 at the y-intercept. Let's look at it. Y equals e to the x. And that's a standard notation. See, if I take a step back here, it tells me what e is, right? See that? E is 2.718281828846, blah, 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 blah. This e is in honor of Euler, who wrote many, many things in the 18th century. He's really one of the most important mathematicians that's ever lived in the Western tradition, for sure. And his work still continues to influence pre-calculus and college algebra to this day. He's really one of the first guys who did a lot of the things he's one of the first people who wrote on the things we're doing in here and kind of the way we're doing it. So in that sense, Euler is still with us. Interesting guy. He was blind like the last so many years of his life, but he still wrote many, many math papers by like a scribe. And he lived to a ripe old age, had a lot of grandchildren, was a born-again Christian. Interesting guy. But anyway, so this black line here is the exponential. And if you just look at this, you can see that right here it goes 2 over and it goes 1 up. So if you zoom in on the black exponential, you can see that the tangent line really has like slope 1. And that's what makes it the exponential function. So if we talk about the exponential function, we're talking about base e. All right, base e defines the exponential function. You notice I used the word "an" over here. That was intentional because there's lots of them. But the exponential function is f of x equals e to the x, all right? And that's a built-in function in your calculator too, right? If you look at it, your calculator's got an e to the x. And it's also got the inverse function to the exponential. So f inverse for the exponential is log base e of x, all right? But this guy is so special that it has its own notation. And so in typical courses like this, we use ln of x. This is the so-called natural log. It's natural because the base e and the natural log come up in all kinds of studies of nature. It's ubiquitous throughout like chemistry, biology, things like that. Yeah? Okay, so enough show and tell. Let me put this away. I hope you top-hatted. So, I mean, I can leave this open and just unplug it if you want. So you didn't top hat yet. Do top hat though. All right, so, what's the graph look like? So for the exponential, let's graph e to the x and the natural log, and let's talk about some typical points on the graph, all right? So that's like the first order of business, is to be able to graph these things, understand their domain and range. So the exponential, you're like, weren't you just doing that? Yeah, I was doing it, but let's do it by hand. So here is the exponential. Right, here's y equals e to the x. The inverse function to the x, first of all, is it 1-to-1? Surely it is, right? Passes the horizontal line test. And so we can get the graph of the inverse function by doing what? By flipping the graph of the exponential over the line y equals x, right? We can also achieve it by flipping points, right? So like 0, 1 maps to what? 1, 0, right? What are two other points on this graph we could flip? We could flip, like over here, there's the point 1 comma e, right? And over here, there's the point -1 comma e to the -1, right? So on the graph of the inverse function, we just turn those tuples, turn those pairs around, right? 1, 0, 1 goes to 1, 0. By the way, what's e to the -1? It's 1 over e, right? So that's about 0.3-ish. It's 1 over 2.7, something like that. Anyway, so this flips to e, 1 over e, all right, -1, which is like down here, all right? And this guy flips to e1, which is like over here. Sorry, my graph is kind of lumpy, but you get the idea. So here we're looking at y equals natural log of x. So let's just take a second here and catalog some values. What do we know? So you guys tell me, what is the natural log of 1 equal to? What is the natural log of e equal to? What is the natural log of 1 over e equal to? These we should be able to do without picking up our calculator, all right? If you have to pick up your calculator to do these, you don't really understand. Of course you can, because you guys have a calculator, right? But look at the graph, right? Y equals log x. The 0.10 being on the graph means the natural log of 1 is 0. This E1 is on the graph, right? E inputted into natural log outputs 1. The natural log of E is 1. E to the -1 inputted into the natural log, -1, right? These are all just special cases, right? These are all just special cases of what? The natural log of e to the x is equal to x again. Right? What's the top case? X equal to what? You're like, 1 isn't e to the x. How do you get e to the x to be equal to 1? E to the x is equal to 1 for what? For what x? Let me write it out here. So my point to you is this: if we put x equal to 0, 1 is equal to e to the 0, right? See that? 1 is equal to e to the 0. That's this y-intercept right here. So the top equation is really x equals 0. This is x equals to 1, right? And this is x equals to -1. These are all examples of this identity. Okay, so there's that. Let's work some more. So where we're going today is I'm trying to get you to appreciate the basic definition of the logarithm, how it interrelates with the exponential. That's our starting point. All right. And once we've accomplished that, then we'll shift and we'll talk about properties of the natural log and how to manipulate equations using the natural log or log-based whatever. All right. So that's where we're going today. All right, so let me shift away here from the natural log and talk about like base 3 for a little bit, okay? So example 1. Calculate log base 3 of the following. You know, via its definition. I also want to put an apostrophe in its. It's not there though, definition. All right, so like log base 3 of 1, I'll start with that. Log base 3 of 9. Log base 3 of, 1/27th. Let's do these. Okay, so log base 3 of 1, this is log base 3 of 3 to the power 0. But then by definition of log base 3, like log base 3 and 3, they annihilate one another basically. They just, when you see them, they think of them as combining in a poof of smoke and just leaving you with 0. Log base 3 of 9, how do you do that? It's what? Log of 3 to the what? Well, 9 is 3 what? So to do these problems, we have to have some number sense. We have to recognize numbers as being powers of the base. Yeah. 3 to the second, right? And then this is equal to? Once you have log base 3 of 3 to the something, the answer is whatever the something is. Just, again, think of these as sort of canceling. What's 1/27th as a power of 3? Can you write it as a power of 3? We can, right? That's that's log base 3 of 3 to the minus 3. 27 is 3 cubed. 1/27 is 3 to the minus 3. So what is that? Well, -3, right?
So you just keep the power 2, basically?
Yeah, you just for these kind of problems, if these are the sort of like the entry level problems, if you can look at the number and understand it as a power of your base, then that's how you do it. So like here's another one. If I have log base 7 of 49, how would I do that? Well, I want to look at 49 as a power of 7. Can I do that?
Log 7.
49 is 7 squared, right? So this is 2. Shall I do another? Okay. Example 3, log base, 15 of 225. There we go. Like, you're just being weird. That's true. Sorry, this is the same example. My bad. What is 15? What is 225? It's 15 squared, yeah? So again, the answer is 2. I'll try to come up with a different example here. Here's a different one. Example 4. Log base 5 of 1/625. What is 625? Come on, everybody knows that that's 25 squared, right? And everybody then knows that this is really 1 over log base 5 of 1/5 to the 4th power, which is log base 5 of 5 to the minus 4 power. So the answer is -4, right? But I think you see that this is a very unstable method, right? Is every number like a power of the base that you're looking at? Like, what if I want to calculate log base 3 of 10? What would I do then? Yeah.
I'm confused. So when you went from 1/25 and then 1/5 to the 4th.
Yeah.
5 to the 4th isn't 25.
25 is 5 squared though. So we have 5 squared. It's 5 to the 4th.
Oh, okay.
Yeah.
Okay.
I could have just said 625 is 5 to the 4th at the start of all this, but listen, so like there are probably some problems like this in your homework, and they're meant to be friendly, easy problems, okay? But they're really not going to help you solve the big bag world of more complicated problems, right? So like, for example, if you come up against, log base 3 of 10, well, you can't do it, right? And many of you, if you look at your calculator, you don't have log base a on your calculator either. So how do you do this problem? If you want to calculate log base 3 of 10, how do you actually do it? There's something called the change of base formula. So change of base formula. So I'm just going to, sometimes I talk about this much later in the presentation, but for you guys, it came up here sort of organically. So here it goes. If we have log base a of x, we can calculate that by taking the natural log of x and dividing by the natural log of a. Now, the change of base formula is often stated not in terms of natural log, but in terms of another base. And like it is generally true that this is also like log base b of x over log base b of a. That's true, but this change of base formula will allow us to calculate like log base 3 of 10 using most calculators. Let me show you how. So what's log base 3 of 10? It would be natural log of 10 divided by the natural log of 3. Natural log of 10 and natural log of 3, those are things you can, pretty much all scientific calculators will do that, right? You might have a scientific calculator that does log base 3 directly. I don't know. Does mine? I don't think mine does. So natural log of 10 is like, 2.30258, blah, 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 blah. And then natural log of 3 is 1.0986, blah, 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 blah. If I divide them in the calculator, then what I get is 2.096 if I just keep 3 decimals. All right? Yep.
What did you do in your calculator?
I punched in natural log of 10 and
How did you punch it?
what kind of calculator do you have? So you do the natural log like that, and then plug 10 in like that, and parentheses like that. There you go.
Thank you.
Uh-huh. Okay, so anyway, this is actually this is an important basic skill. How do you actually calculate values of the log base whatever? This is how you can do it, right? So let's shift back here and let me talk to you more about properties of the logarithm, all right? So what are the properties of the logarithm? Because once we know properties, then we can do some more. I'm going to try to do more examples without the calculator. The idea is not to use the calculator to do everything. The idea here is to really understand the properties by doing some arithmetic. So here's the properties of the logarithm. All right, so number 1, log base a of x times y is equal to log base a of x plus log base a of y. Property number 2, if we have log base a of x over y, well then we have log base a of x minus log base a of y. And then there's another one, 3. If we have log base a of x to the power p, that gives us p times the log base a of x. Right? And then, of course, we also have the defining properties, right? What were the defining properties? We have log base a of a to the x equals to x, right? And a to the log base a of y equals to y. This is for any x in the reals. And this is for y in the positive reals. Now, I wrote it with log base a, but all of these things are true. This is for a greater than 0, a not equal to 1, right? We need to assume that about the base. And I will tell you this, on the test, I will not test about base less than 1 in terms of logarithm. Like I've never tested students on like log base a half for the test. It might come up in some obscure homework problem, but pretty much nobody talks about fractional bases as far as I've ever seen. I almost always think of the base as being greater than 1. I'm sure there's some person somewhere who has a reason to talk about fractional bases, but I try to avoid them because I want to focus mostly on the case a is greater than 1. In fact, mostly I focus on the case of a equals to e. What do these things look like? If we put a equals to e, all of your log base a does what? If we choose a equals to e, you replace log base a with natural log and replace a with e in the above. All right? So let's put these into practice. Let's calculate some things, yeah? So example 6. And by the way, I really should prove all of these things for you at some point, but I think if I prove them at the start, it's kind of overwhelming. I think it's better to do examples, get used to these properties, and then we'll circle back and prove them if there's a good time and space to do it in a future lecture, yeah? I will tell you this though, the reason that they're true is that they're just the logarithm version of power, like exponential laws that you already know. Wait a minute, do you already know laws of exponentials? No. Maybe not. So let's talk about that. What are the laws of exponents? Probably should talk about that a little bit, shouldn't we? So if we have a to the x times a to the y, we get a to the x plus y. That's one. Another one that we have is if we have a to the x over a to the y, we get a to the x minus y. And then there's also this one. If we have a to the x to the power p, we get a to the, well, xp. So these are some important laws of exponents, right? Common special cases are what? Like a to the 0 is what? It's 1. A to the 1, a. A to the minus 1, 1 over a, right? Those come up a fair amount. Okay, so there's your walk down memory lane in terms of how the laws of exponents work, yeah? We'll be using these in examples, so I wanted to put them back out here before we play with them. Example 6 then. Okay, so what if we wanted to calculate, say, log base 3 of 54? Wait a minute, 54? Give me a second here. I got to think about something. 36. Now, yes, we could be boring. We could go to our calculator and do natural log of 36 divided by natural log of 3, and we'd be done with it. That would be the number, right? True. We could calculate this using change of base formula, right? But let's not do that, yeah? Oh yeah, see, I was actually trying to tempt you guys with this. Maybe we're going to have to do that, actually. Ah, curses. Sorry, I was thinking of something, but I think I was thinking wrong. Aw. I tempted myself with something which was totally bogus. Here, let me show you my temptation, which was that this is really, so don't do this, okay? This is a cautionary tale. I was thinking, well, 36 is 9 plus 27, right? And then, I could do log base 3 of 9 plus log base 3 of 27, right? Which would be log base 3 of 3 squared plus log base 3 of 3 cubed, which would be 2 plus 3, which would be 5. And I thought, this is a cool example. There's just one problem with it. What's the problem? So you guys like to do this. Square root of like 10, right? You're like, I know the square root of 10. It's the square root of 1 plus 9, right? Which is the square root of 1 plus the square root of 9, right? Which is then 1 plus 3, yeah? So the square root of 10 is 4. Is this true? I hope you realize this is not true, right? Where's the lie, right? Which step here? Yeah.
It should be, they have a log 3 and 9 and log 3, 27 on the second step.
Yeah.
It should be times and not plus, because if you look at the first log, it's exponents.
Okay, right.
Separated.
So what you're saying is this step right here, this is no. No, you cannot do that. Just like you can't do this either, right? You're more familiar with this being a no, right? Because you've already been scolded for that at various points in your mathematical existence, right? Somebody said, no, you can't do that. I wish you could. I mean, if you could, things would be so much easier, right? You just cut through square roots like they're nothing, right? But it's not how it works, unfortunately, right? The square root doesn't allow you to break up over a sum, and neither does the logarithm. There is, unfortunately, and here's the bad news, guys, there is no nice property for additive, like a sum in a logarithm. It doesn't simplify. All right? So like there's no, this does not, to quote my community college professor, this dog does not hunt. All right? Like you cannot do this. So how to calculate log base 3 of 36? 6 times 6. So at the moment, for us, I think we have to fall back on my change of base formula. But you're right, there's a lot of different ways we could do it. Okay, let me look at a couple different ways of calculating log base 3 of 36. Let's look at a couple different ways. So again, just to be clear, no, okay?
So it's not 5.
It is not 5. And that one is not 4. That's also true. Yeah, please don't let me be the, but Dr. Cook said that I could break up the square root like that. We learned it. Okay, so let's talk about, let me show you a couple different ways we can calculate log base 3 of 36. Okay, so the most boring and sort of uninspired way of doing it is to use my change of base formula idea again, right? I can just go, okay, well that's going to be natural log of 36 divided by the natural log of 3, which is whatever that is, right? And so you have some homeworks which are going to require like an exact approach. And the homeworks which will require an exact approach, you're not going to be able to solve in this way. You're going to have to use like, well, exact methods, which is to say you're going to have to use the identities for things. Natural log of 3, I just wrote over there. 1.0986, blah, blah, blah. Anyway, you work that out. What we got is 3.262. I'll just keep 3 decimals. Let me show you a couple different ways to look at that number besides that. Yep.
Can we
Also do what?
Is that always going to end up being a decimal answer? Or
Well, yeah, any fraction we can write as a decimal, yeah. As long as we're not dividing by 0, right? It is interesting, right? Decimal numbers we take for granted, but they're actually not that old. Like, the existence and notation of decimal numbers, it only predates Newton by about like 50 years. Some guy named Stephen come up with them. And without decimal numbers, you can't really do calculations of arbitrary precision, right? Like, if I give you two fractions, right, like 10/17 and, 13/29, and then I say which one's larger, which one's smaller, you'd have to really stop and think about it, right? But if I give you two decimal numbers and I say which one's bigger, which one's smaller, you just look at them and you go, oh, well, that one's bigger, that one's smaller. You can just see in the decimal numbers the ordering. Whereas with fractions, and I'm now digressing. So let's get back here. So my bad. Log base 3, 36. Another way I could do this, 36, it is 4 times 9, right? So we could also write this as log base 3 of 4 plus log base 3 of 9. Now log base 3 of 9 is nice, right? Log base 3 of 9 is log base 3 of 3 squared, right? And so this log base 3 of 4, I could also write as log base 3 of 2 squared, yeah? So this we could simplify as 2 times log base 3 of 2 plus 2. And then how would you calculate log base 3 of 2? See, at some point or another, we're going to be driven back to the change of base thing unless we've got a calculator that does log base 3. There's just no nice way to calculate something like this. Yeah, so this would be 2 times the natural log of 2 divided by the natural log of 3 plus 2. What?
Why would that become 5 squared? Shouldn't that be 3 squared?
Ah, I'm a dummy. So thankfully, I had 2 errors. So they canceled out and gave me something right. But yeah, I meant 3 squared. Thank you. All right. So one way to look at this is this. If I said write log base 3 in terms of natural logs of numbers, this would be the answer, you know? Well, this is one answer. What's another answer? Of course, if I just wanted to express log base 3 in terms of natural logs of numbers, I could also write this. That's actually kind of interesting, right? That those two numbers are equal. I mean, at first glance, do they look equal to you? They don't, maybe not at first glance to me either. But that's the thing, is there's properties of natural logs that allow you to simplify them in sometimes surprising ways. All right, let's go on here. Let's solve some equations before we part for today. So suppose you want to solve, where am I? Example 7. Let's see here. How about we want to solve 2 to the x squared equals 2 to the, 5. How would you solve such an equation? There are various ways of going about it. One way you could do would be like, oh, by the one-to-one property of the exponential function with base 2, we can see that x squared equals to 5. But let me show you another way. What we can do is we can take log base 2 of the equation. See, if I take log base 2 of 2 to the x squared, I get log base 2 of 2 to the power 5. Now, what happens? These are inverses of one another, right? So I just get x squared equals to 5. Can you guys solve x squared equal to 5? What are the solutions? square root of both sides, right? So we have x equals 2 plus or minus the square root of 5 is the answer there. So there's an example of a exponential equation. And we can use the logarithm to solve it, right? One more here and we'll be done for today. Example 8. You might run up against something like e to the x times e to the 2x equals to, oh, I don't know, 10. Solve that equation. How would you solve this equation? So here we're going to use laws of exponents. To combine these two, this gives us e to the x plus 2x, which is 3x, equals to 10. All right? How do I solve an equation involving e to something? The answer is take the natural log of both sides. Right? So we take the natural log of both sides. And how does the natural log work with the exponential? Remember, they're inverses. So you just get back out the argument of the exponential, which is 3x here. So we get 3x equals natural log of 10. And therefore, solution, x equals to natural log of 10 over 3. And there you go. So a lot of times, we're content, we're happy, in fact, to have answers in terms of natural logs, all right? Like answers don't always have to be decimals. I was just showing you some decimals to make it more concrete. And I'm sorry, I think I've spent too much time on the decimal thing today. My bad. But anyway, what's done is done. So enjoy the rest of your day.